The program from our last lesson was a little boring. I mean, aren't we programming in 3D? It looked pretty 2D. Well, let's make it more interesting by using transformations and timers to have our shapes spin in 3D. So the way that transformations work in OpenGL is it's kind of like you have a bird that starts out at the origin facing in the negative z direction, and this bird can move, rotate, and even grow and shrink. It's sort of flying around our 3D scene. And whenever you specify a point to OpenGL using GL vertex 3f, this point is relative to the bird. So, for instance, if we were to shrink our bird by a factor of 2, and then move it 2 units to the right from its perspective, then the point 0, 4, 0 relative to the bird would actually be at the point 1, 2, 0. And I'll show you another example. I have it right here using my bird that I made out of silly putty. And we're viewing him from the side. This is the positive z direction, just so we can see things more clearly. So I'm going to take this bird and rotate it 90 degrees. And then I'll move it 2 units up from its perspective. So that's a translation of 0 to 0. And now, if we take a look at this point right here, 1 unit in front of the bird at 0, 0, negative 1 relative to the bird, that point is actually at 0, negative 1, negative 2 in world coordinates. And I have a little picture right here which lays everything out nice and clearly. So that's the idea behind transformations. And what I'm going to do is take this right here. This is the code from the last lesson, except I removed some of the comments. And I'm going to, first of all, I'd like to point out this right here, this GL load identity. What it does is it resets the bird, so it's at the origin and facing the negative z direction. So what I'm going to do first of all is all of these negative 5s, the z coordinates, I'm going to, instead of doing negative 5 everywhere, I'm just going to translate the bird forward 5 units by calling GL translate f with negative 5 for the z coordinate. And I'm going to change all of these negative 5s to zeros. So the program will look exactly the same when we're done. This is just another way of doing the same thing. And in fact, you might even be wondering why we're doing transformations at all. Why don't we just specify the points directly? Well, that should be clear by the end of this lesson, after we're done. So I'm just changing all of these to zeros, and I want to build the project, and then we'll run it. So here it is. It looks exactly the same as before. It's just done a different way. And now I'm going to add another thing. I'm going to translate to the center of the trapezoid before I specify its points. So I'll just add a call to GL translate f right here. So I'm going to translate down 1 unit to the center of the trapezoid. And then I'm going to change these coordinates right here so that it's drawn in the same way. And actually, what we're going to have to do is we're going to have to save the transformation state right here by calling GL push matrix and restore it down here at the end using GL pop matrix. So, by the way, this name right here, matrix, it comes from the fact that OpenGL uses matrices to represent transformations, and you don't have to know how it does that. I just thought you might want to know where these names come from. And so we have this call right here, which saves the transformation state, and for every call to GL push matrix, we need a corresponding call to GL pop matrix to restore the transformation state. So now let's do the same thing down here with the pentagon. We're going to save the transformation state and translate to the center of the pentagon, which is at 1, 1, 0. And then I'm going to take these coordinates right here and change them up so they are relative to the center of the pentagon. And just gotta change all these numbers real quick. And that's what we're doing for the pentagon. Now we're going to do the same thing for the triangle. And actually what I'm going to do is I'm going to take the one call to GL begin, GL triangles, and split it up into two calls. So I'm going to do GL end here, and down here GL begin, GL triangles. And the reason I'm doing that is because you can't call transformation functions in between a call to GL begin and GL end. You have to do it outside. So for instance, we need this GL pop matrix right here. And also you should note that GL push matrix and GL pop matrix, we don't just get one transformation state that we can save. We actually have a whole stack that we can use of at least 32 different transformation states that we can save. And every call to GL push matrix puts one on the top of that stack, and every call to GL pop matrix will take the transformation state at the top of the stack and restore it and remove it from the stack. So that's what's up there. And right here I'm going to translate to the center of the triangle at -1, 1, 0. And then change these coordinates right here to match. So again, this is just another way of doing the same thing. Our program should look exactly the same once we run it. And let's take a look. There it is, our trusty old polygons. So now that we've done all that, I'm actually going to put a change in. I'm going to rotate those three shapes by 30 degrees. So I'm going to have a variable here, 30 degrees. That's the amount we want to rotate by. And in order to rotate, we're going to want to call GL rotate F. And the first argument is the amount by which we're rotating in degrees, and the next three arguments are the axis about which we're rotating. So I'm going to rotate the trapezoid about the z-axis by angle degrees. And let's also rotate the triangle by the same amount by another call to GL rotate F. Only this time it's going to be about the y-axis. Sorry, that was the pentagon, not the triangle. And for the triangle, I'm going to rotate it again by this same amount, only I'll do it about this weird vector, the 1, 2, 3 vector. That's the axis about which we're rotating. And let's build this project so that we can see what it does. And here we go. These shapes are now rotated a little bit in 3D, which is kind of cool. And now what I'm going to do is I'm going to rotate the camera to the left by 10 degrees so that we see the scene from a little bit of a different angle. So I'm going to have another variable up here, which is the camera angle, and set it to 10. So actually we're going to be using a special trick to do this. Instead of rotating the camera angle, we're actually going to rotate the whole scene backwards. So we rotate by the opposite of the camera angle, right here, about the y-axis. And this is a common trick to use in OpenGL, actually, rotating everything the opposite direction instead of rotating the camera. And once I do that, here we go. Everything looks like it's a little bit to the right because the user is viewing the scene to the left a little bit. Or at least that's what it's supposed to look like. And now, actually, I'm going to take the pentagon and make it a little bit smaller. So I'm going to change it to 70% of its original size by calling GL scale F. And I'm going to scale it by 0.7 in the X, Y, and Z directions by this call right here. So let's take a look. We'll build the project and run it. So now this pentagon is a little bit smaller. And that's what the call to GL scale F did. So actually, I'm going to change this camera angle back to 0 just so we can see everything better. And finally, we're going to use timers to make these shapes rotating continuously. So we'll actually have some motion in our scene. So right here, I'm going to add a function called update, which is going to be called every 25 milliseconds. And it gets this integer parameter, which I'll explain in just a second. And what we want to do is increase the angle by 2 degrees. And I'm also going to, right here, make it so that if the angle is bigger than 360, we're going to subtract 360 from it, which makes it the same angle, but it's closer to 0. And you don't actually have to do this. You could have an angle of 480 and OpenGL would be just fine with it, but I'm doing this for reasons of floating point precision, which I'm not going to explain exactly. Just know that it's good to have angles that are close to 0. So then we have to add a call to glut post redisplay, which tells glut that the scene has changed and that it has to draw it again. If we don't do this, OpenGL, or rather glut, will not redisplay, or it won't redraw the scene. And finally, a call to glut timer func, which is going to tell glut to call update again in 25 milliseconds. And this 0, that's the value that this value parameter gets, and we're not really using it. We don't really care about it, so I'm just going to make it 0. And finally, I'm going to take this line right here and copy it. And down here at the end of the main function, I'll put a call to GL timer func, so that will call update 25 milliseconds after the program starts. And now let's take a look at what we have done. What have we created? Let's see. There we go. They're spinning in 3D. Looks kind of cool. It's pretty nifty for just the second lesson. We have some spinning shapes right here. And there we have it. And there's one more thing I'd like to explain, actually. I kind of didn't really go over this last lesson right here where it says GL matrix mode, GL projection. It changes it so that our transformations are actually used for this special projection matrix mode. You don't really need to worry about what it does. It just makes it so that we have 3D perspective. So in the draw scene function, we need to change back to GL model view, which is the normal matrix mode. So this is just used when we're resizing the window. And by the way, this projection matrix mode is sometimes described as the camera angle, which is not accurate. You don't want to use it for the camera angle for a few different reasons. For instance, the lights do not move with this transformation. So we're just going to ignore that little trick or way of doing things because it's the wrong way of doing it. And that's how transformations and timers work.